Hello, Rodriguez. Can you hear me?
Yes, sir.
Okay, so I'm going to go over the quizzes that are due today, and I chose some questions, but obviously you can ask me if you have like any specific questions. Sorry about that. We're about to leave though. Okay, so we are going to have questions like this where you're asked to determine the exact value. One thing I have to say is that you have to know the domains and the ranges of the inverse trigonometric functions, and you can refer to the notes. I may not like write all of them, but the inverse function arcsec, so arcsecant, its restriction is 0 to pi over 2, then union pi over 2, and then pi. Note that this at the end it is closed, but it is open here. So which means pi over 2 is not part of the restricted interval. So what does that mean? 0 to pi over 2, that is from here up to here, then pi over 2 to pi, that is up to here. So what that means, the arcsecant lies in quadrant 1 and quadrant 2 apart from the point pi over 2, okay? Now, so if I have something like this, then what they are asking for is, can you find an alpha such that it is equal to the secant of square root over 2? And when I have that, this means that sec alpha is equal to square root over 2. Now, we've determined that that it is in the 2 quadrants, but check that in this particular question, secant of alpha is positive, right? So we know that here all of them are positive, and then here only sign is positive, but secant is related to cosine. In fact, I can write this as 1 over cosine alpha is equal to square root over 2, and this means that cos alpha is 1 over square root of 2. So maybe now, since I have changed to cosine, so you could determine alpha from here. If you change to cosine, then you know that the range of arc cosine, or the restriction of arc cosine, is 0 to pi, and 0 to pi, it remains the same thing right here. So it is in these 2 quadrants, but cosine of alpha is positive, and therefore we are very sure that we have to find that angle in the first quadrant. And that alpha, for which the cosine is 1 over square root of 2, is right there, okay? So which means that this alpha is the same as pi over 4. So what we are saying, therefore, the secant inverse of square root over 2 is equal to pi over 4. So I just wanted to remind you that for every inverse trigonometric function, you have to find the restriction so that you don't find an angle which is out of the required interval. Okay. Okay. To find the restriction, find the expression of secant y, given that y is equal to arc tangent of 7x. When I have y is equal to arc tangent of 7x, then it means that tangent of y is equal to 7x. And this is where you can use the help of the triangle method. So we have a right angle triangle with angle y, and this is a tangent, and from the trigonometric formula that we know, which we can write as that, we see that tangent is opposite over adjacent. So I have tangent of y is equal to 7 over x, and therefore in my triangle this is the same as 7x, and then which is the opposite, and then the adjacent is 1. And from Pythagoras theorem, I can tell that this is 1 squared, which is 1 plus 7x squared, then the whole of it under a square root. Okay, now from here we can determine secant y, and secant y, like we said above, it is the same as 1 over cosine y, and therefore I can find the expression for cosine y, and cosine y is the same as the adjacent over the hypotenuse. So cosine of y from the triangle, so from this triangle here, cosine of y is the same as the adjacent, which is 1, then over the hypotenuse, which is 1 plus 7x squared, that is 49x squared, and the whole of it under a square root. And therefore, my secant of y is equal to 1 over the whole of this answer, which is just 1 plus 49x squared and a square root. So why I chose this is because I just wanted to remind you of the triangle. In some cases, even when you take derivatives, you're going to need this triangle. Okay. Then the next one, that I chose, we want to find the derivative of the tan inverse of x plus 6. Now, I want to remind you that whenever I have the derivative of arc tan of u, where u is a function of x, then this is the same as you take the derivative of u with respect to x, then you divide by 1 plus u squared. Now, if you remember this, then life becomes easy. Of course, if you don't remember this, but you remember how to differentiate that from scratch, then that's completely fine. But first, if we apply this formula, then we are taking the derivative of f, but f is the tan inverse, which is arctan of x plus 6 where x plus 6 is our u in this case, right? So what this derivative is telling me is that you take the derivative of u, so you take the derivative of x plus 6, and then the whole of it over 1 plus u squared, so 1 plus x plus 6 squared, okay? So therefore, if I have my function as tan inverse of x plus 6, then the derivative from this formula is the same as take the derivative of x plus 6, which is just 1, then divide by 1 plus u squared, which is x plus 6 squared, okay? And this is 1 over 1 plus x squared plus 12x, then plus 36, and this is 1 over x squared plus 12x, then plus 37. Now, like I said, if you remember this formula, then everything becomes easy. But just for this example, I'll show you an alternative. So alternatively, if I have this function, which I can call y, and is the same as the tan inverse of x plus 6, then when I take the inverse both sides, then I'll have tangent of y is equal to x plus 6. And now I can differentiate both sides with respect to x. And therefore, I'll have, when I differentiate tangent of y with respect to x, then I get sec squared y, but I'm respecting x, so this is dy dx. And when I differentiate x plus 6 with respect to x, I just get 1, okay? And therefore, my dy dx is just 1 over secant squared over secant squared y. Now, like we said above, 1 over cosine is secant, so 1 over secant is cosine, and therefore 1 over secant squared is cosine squared 1, okay? So once again, I can now use my triangle from this expression. We have tangent of y, so our angle is y, and like we said, tangent of y is opposite over adjacent, so my opposite is x plus 6, and my adjacent is 1, and therefore this is x plus 6 squared under the square root from Pythagoras theorem. Okay, so from this triangle, it means that dy dx is cos squared, but cos squared, cosine is the same as adjacent over the hypotenuse. So my adjacent is 1, and my hypotenuse is x1 plus x plus 6 squared, and the square root, but that is just the cosine, and I'm squaring it, so the whole of this guy will be squared. And you see that when I do that, I'll get 1 over the square root will cancel with the square, so I just have exactly the same thing that I had before, which is x squared plus 12x, then plus 30 plus 37. So what I'm saying is that it's very good that you remember this, how you take the derivatives of all these inverse trigonometric functions, the arc cosine, arc sine, arc tangent, arc secant, and all that. But if you don't remember that, then you can use this alternative and you can take the derivative from scratch. The order is simple. Just take an inverse both sides, so you have the real trigonometric function, differentiate both sides. Most of the times you're going to know how to differentiate whatever. It can be cosine, it can be sine, and use your triangle that you have from the expression, from whichever expression you will have, and make sure that your answer is back to x. That is the whole reason we use a triangle, because this answer is in y, but we need our answer in x. So that's why I use a triangle to make sure that everything is back to x. Okay. 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 Same thing. We want to differentiate this. So now this one we can do it all at once. From our previous discussion, the derivative of the natural log, remember what we do. If this is u, then the derivative of the natural log is u prime over u, right? So my function has that, so which means my derivative of this function will be, you differentiate this function inside, but this function is arctangent, and the derivative of arctangent, we just said it is u prime over that, right? So where my u is 3x plus 7, so take the derivative of 3x plus 7, which is 3, divide by 1 plus 3x plus 7 squared. This is just from the formula. Take the derivative, then divide by 1 plus u squared. Okay, now that is the derivative of this guy inside here. But the derivative of the whole function requires that after taking this derivative, you divide by what you've differentiated exactly. So this guy, the whole of the answer I have, which is the derivative of the arctangent, I divide it by what I have differentiated, which is arctangent of 3x plus 7. Rodriguez, is that fine?
Yes.
Okay. So I can simplify this, and this is the same as 3 over 1 plus, when I open up that one, maybe that's 9x squared. So this is 3x plus 7 squared, and since I'm dividing by that, this guy here will multiply by arctangent of 3x plus 7. And you can simplify it further if you want. You can open up this bracket, and when I open up, maybe we can do that. So this is the same as 3 over 1 plus 9x squared plus 2ab, so that is 2 times 3, which is 6, 6x times 7, which is maybe 42, so 42x, then plus 49, and the whole of this guy is multiplying with arctangent of 3x plus 7. Okay, so this is 3 over 9x squared plus 42x plus 50, then times arctangent of 3x plus 7. Okay. Okay, so finally, for me, according to the questions I chose, finally, this was one example where the natural log is outside. So I first use the rule of natural logarithms for differentiation, which says that you take the derivative of whatever is inside, then divide by the same exact function. Right now we have the natural log inside. Maybe I have to remind you that if I have d dx of arctangent of u, this is u prime over 1 plus u squared. So right now, if you're very, very careful, our u is natural log of 9x plus natural log of x, 9x plus 10. So that is the derivative we are taking. So f prime of x is the same as u prime. So the derivative of this, that is 9, then divide by 9x plus 10. That is how we take the derivative of the natural log. Then divide by the whole of that answer. We divide it by 1 plus u squared, but my u is this. So u squared will be natural log of 9x plus 10, and the whole of this is a square. Once again, I can write this as 9 over 9x plus 10, and then this is times 1 plus natural log. I can put the square here, 9x plus 10. Okay, I hope that is fine. Okay, before I move on to quiz 26, maybe let me remind you. So once again, the restriction for arc sec is this, then we have as cosine as 0 to pi, then negative pi to pi for arcsine. Arctangent is also negative pi to pi, but check, for arcsine, the endpoints are included. For the arctangent, the endpoints are not included. Arccotangent is almost the same as arccosine. Arccosine, we have endpoints included, and arccotangent, we have the endpoints not included. Okay, maybe just a quick one. Let me remind you, in case you come back to look at this, d dx of arcsine of u, that is the same as u prime over 1 minus u squared and the square root d dx of arc sec u, that is u prime over u, then square root of u squared minus 1, and the arc cotangent may be d dx of arc sine of u, not sine but cosine a cosine of u is negative u prime, then over 1 minus u squared. And I wrote for the one for arctangent right here. Okay, just in case you come back to look at this. Okay, Rodriguez, any questions in quiz 25 you think I should look at and I haven't looked at them?
Um, not right now. I don't have any
Okay.
questions for that one.
Okay. Okay. So then let's move on to quiz 26, and quiz 26 is all about hyperbolic trigonometric functions. So I think the most important is we have to remember their relations. So the cosine hyperbolic of x is e to the x plus e to the negative x, then over 2. The sine hyperbolic of x is e to the x minus e to the negative x, then over 2. Of course, the tangent hyperbolic is sine hyperbolic over cos hyperbolic, then sec hyperbolic 1 over cosine hyperbolic, just like we know them in cosine, sine, tangent of x. Okay, and when you check your notes, sine hyperbolic is an odd function with a domain negative infinity to infinity, so the whole real number line. And cos hyperbolic is an even function with the same domain. Maybe some important relations we should remember is that cosine hyperbolic of x minus sine hyperbolic of x is e to the negative x. Cosine hyperbolic of x plus sine hyperbolic of x e to the x, and cosine hyperbolic squared of x minus sine hyperbolic squared of x, that is 1. Please note that for cosine, for the usual trigonometric functions, the first ident has a plus, but for the hyperbolic functions, it has a minus. Now, knowing this can save you some time, especially when you're working around some questions. But you should be, if you remember this, you should be able really to prove all of this, and by just substituting this guy here and this guy here, wherever we have sine hyperbolic and cosine hyperbolic. Okay. There is also a list of their derivatives. Once again, it is good to remember those derivatives, those expressions, but if you can't, but you remember these two guys, you can, at least we know how to take the derivative of an exponential, so you can always substitute wherever there are these guys, you substitute their equivalents and take those derivatives. Okay. Okay, so for this particular question, we have that f of x is 3 sine hyperbolic of 6x. I realize that we need to take a derivative of this, so you can take the derivative right here, or you can first change this function or modify it so that you write it in terms of the exponential. So this is 3, then times sine hyperbolic, but I say that sine hyperbolic is the same as e to the power whatever angle you have there. In this case, this is 6x, then minus e to the negative 6x, and the whole of this is over 2. Okay, I need to calculate f of 0. So my f of 0 is 3 over 2 e to power 0 minus e to power 0, and that is 0, because e power 0 is 1 and e power 0 is also 1. Then I need to take the derivative of this function here. 3 over 2 is a constant. When I take the derivative of e to the 6x, hope we remember that, that is 6e to the 6x, then minus, which is that minus there, take the derivative of e to the negative 6x, that is negative 6e to the negative 6x. Okay, these two here, I brought it outside. So therefore, this one becomes a plus, and I have a common 6, so I can bring the 6 outside if I want, and this is times 6 into e to the 6x plus e to the negative 6, the negative 6x. This can reduce this by 3. So finally, I need to find the f prime of 0, which is 9 into e to the 0, then plus e to the 0, and this is 9 times 2, which is the same as 18. Now, take that this is when I choose to get this function and I change it to the exponentials right away. The other thing I can do is, like I said, we know the derivative of sine hyperbolic. So the derivative of sine hyperbolic, maybe just right here. So alternatively, if I have my f of x as 3 sine hyperbolic of 6x, the derivative of sine hyperbolic is cosine hyperbolic, but I have a 6x here, so I'll do some chain rule as usual. So the derivative of this function is 3 is a constant. Okay, take the derivative of sine hyperbolic, that is cosine hyperbolic, right? Keep the angle the way it is, then times the derivative of that angle. That is how chain rule works. So the derivative of that is just 6. Okay, so which means this derivative is 18 cosine hyperbolic of 6x, right? So if I have this as my f of x, then my f of 0 is 3 sine hyperbolic of 0. 6 times 0 is 0. And if I have this as my derivative, then f prime of 0 is 18 cosine hyperbolic of 0. Now, I have f of 0 plus f prime of 0, that is what they are asking for. And this is 3 sine hyperbolic of 0, then plus 18 cosine hyperbolic of 0. And now you can now bring your exponential. So what I'm showing you is that you can first write the function in terms of the exponentials and then take a derivative, or you can take the derivative, and after knowing the derivative, you change the function to the exponential. So this is 3 into e to the 0 minus e to the 0 over 2, then plus 18 into e to the 0 plus e to the 0 over 2. And this guy is 0. And this guy is 1. And you see that we end up with the same answer. I hope that is fine. Okay, fine, maybe not finally. So we have this, I chose this because so we have the tangent hyperbolic. So this is where it is really, really important, because tangent hyperbolic, well, I know that it is sine hyperbolic over cosine hyperbolic, right? Now, this guy in terms of the exponential, I know what it is. This guy in terms of the exponential, I know what it is, right? So I can do that and then divide the two of them. And then after that, each of them has that angle. So, and then I can take the derivative. But you can see, you realize how that can be a little hectic. So that's why I'm saying that if you really know that d dx of tan hyperbolic of x is the same as sec squared, sec hyperbolic squared of x. So if you know that derivative, then life becomes a little easier, okay? Now, so we have our function as tan hyperbolic of 7 to the 5x. Now we have to do some chain rule here. So the derivative of this is, by chain rule, the derivative of tan hyperbolic is sec hyperbolic squared. We keep the angle the way it is, right? Then times the derivative of this angle. I hope we remember how to differentiate that from our previous discussion. So to differentiate this, if you remember very well, it is the same as the derivative of the guy in the power, which in this case is 5, right? Then keep the same function the way it is, then times the natural log of a, and this, in this case, our a is just 7. Okay, so I can rearrange this nicely, and I have this as maybe 5 times 7 to the 5x times natural log of 7, then times sec hyperbolic squared of 7 to the 5 5x. Okay, maybe we can choose so same thing here. You can take the derivative right away. Maybe we can do one for product rule. Okay, maybe this can be my last one for me. As usual, this is product rule. So once again, let us see what happens if we do it in two ways. So the first way is you can take the derivative directly. Once again, the derivative of sine hyperbolic is cosine hyperbolic. The derivative of cosine hyperbolic is sine hyperbolic. Please remember that. In the usual trigonometric functions, the derivative of cosine is negative cosine, but the derivative of cosine hyperbolic remains sine hyperbolic, okay? So therefore, by product rule, this derivative is 3. 3 is a constant, so I can just keep it. And so by product rule, I hold sine hyperbolic of 4x, and I differentiate cosine hyperbolic of 4x. Now, remember there is some chain rule here. So the derivative of this is sine. I keep the angle, and then times the derivative of this 4x, which is 4. So this will be 4. This will be 4 sine hyperbolic of 4x. Okay. Then plus, by product rule, hold cosine hyperbolic of 4x times the derivative of sine hyperbolic of 4x, which is 4 cosine hyperbolic of 4x. Okay. So this is 3 into 4 sine hyperbolic squared of 4x, and then plus 4 cosine hyperbolic squared of 4x, and I can write this as 12 into sine hyperbolic squared of 4x, then plus cosine hyperbolic squared of 4x. Once again, this guy does not add up to 1, okay? This guy is never equal to 1. Now you see that when you remember these derivatives, then life really becomes easy, especially if someone has not specified that you write your answer in exponential form. But what I'm saying is that even when we do this by first writing our function in exponential form and then we take the derivative, you should be ending up with the same answer, but it might end up being more work, but for sure you end up with the same answer. So f of x is 3 sine hyperbolic is the same as e to the 4x minus e to the negative 4x, then over 2. Okay. Then times e to the 4x plus e to the negative 4x, then over 2. We are multiplying everything, so this 2 and this 2 can multiply to make 4, then so this guy can be 3 over 4 into e to the 4x minus e to the negative 4x, then times e to the 4x plus e to the negative 4, e to the negative 4x. Now, you can do this, you can first multiply this, but maybe that's not a good idea. I can first multiply, open up these brackets maybe. I'm not saying that is the only way you can do it, but let me do that. So e to the 4x times e to the 4x, remember when we multiply same bases, then we add up this guy, so this will be e to the 8x, right? E to the 4x times e to the negative 4x, that is e to the 4x minus 4x, so that is e to the 0, which is 1. So this is plus 1, right? then minus 1, because this is e to the negative 4x times that guy here, then minus e to the negative times e to the negative, that is e to the negative 8, the negative 8x. So the 1 and 1 can cancel to give us a 0, and therefore this is 3 over 4 e to the 8x minus e to the negative 8, the negative 8x. And you see how if I open up brackets, I remain with something a little easy. So when I take the derivative of this is 3 over 4 as a constant. This is 8 e to the 8x plus 8 e to the negative 8x. By now, I hope you know how I get that. So this is 3 over 4 times 8 outside e to the 8x plus e to the negative 8. And this one will go 6. So this is 6 into e to the 8x plus e to the negative 8x. And we should be able to determine, if I continue and simplify this guy here, I should be ending up with exactly the same answer. Remember this guy here, when I square it, it is e to the x, e to the 4x minus e to the negative 4x over 2, and I square the whole of it. So this is 1 over 4 into e to the 4x minus e to the negative 4x, and you square. Now, you remember how to square this. So this guy will be, maybe, let me just open up one of these guys, okay? I won't open up this, let me just open up this. So what I'm saying is that sine hyperbolic squared of 4x is the same as e to the 4x minus e to the negative 4x then over 2, but we are squaring the whole of this, and this is the same as 1 over 4 into e to the 4x minus e to the negative 4x, but this is squared. This is 1 over 4, right? Now square those guys. It is e to the 4x squared, which is e to the 8x, minus 2 times this, which is e to the 0, which is 1. 1 times 2, that is just 2. Then plus e to the negative 8x. Okay? I hope that is fine. Then the cosine hyperbolic squared of 4x, that is the same thing, 1 over 4 into e to the 4x plus e to the negative 4x, but this is squared. So this is 1 over 4 into e to the 8x plus 2ab, same thing, so that is 2, then plus e to the negative 8a. So what we are doing is we are adding up this guy and this guy here in this expression. So finally what we have is 12 over 4, and when we add up these two expressions, I see that the 2 and the negative 2 will go. This will add up with this to give me a 2. This will add up with this to give me a 2. And therefore, the 2 will come here, then times e to the 8x plus e to the negative the negative 8x. I hope we did not make a mistake somewhere. So by this, that is 2, by this, by that, that is 6. And finally, we have 6 into e to the 8x plus e to the negative 8x. And you can see that we end up with exactly the same answer. So whatever you find easier, but what I'm saying is that all that I'm saying is that you can first take the derivative and then you substitute the exponentials in the derivative, or from the function you can change everything to the exponentials, and then after doing that you can take the derivative. Okay, is that fine?
Yes.
Okay, so finally for me, let me mention this, that whenever I have an exponential, in red maybe, whenever I have an exponential to the power natural logarithm of anything, so let's say of a, then that is the same as a. Don't forget that there are some cases where you're going to find yourself needing that. For example, yes, but you're going to find cases where you're going to require to use that. Okay, so if there are no questions, Rodriguez, for me, that's it. Thank you so much for joining.
No, there's no questions. Thank you for teaching me.
Okay. See you on Thursday. I hope
See you.
you join on Thursday.
Have a good week.
Okay, bye.